Second experiment is tuning and closed loop control of flow process. Flow process means it controls the flow rate. In the first experiment, we have seen level process. Level process. In that one control valve is there. The flow rate is adjusted by the pneumatic signal, that is 3 to 15 psi. Pneumatic signal is used for that. I to P is used, and before that one controller is there. This is the controller that gives 4 to 20 milliamps. 4 milliamps means valve is completely closed, zero flow rate. 20 milliamps means fully open, 100% flow rate. In other words, 3 psi means fully closed, 15 psi means completely open. For that, we have to measure the level. A level transmitter is there. Already I have seen a DPT is used to measure the level. And it is compared with the set point. Set point is given to the controller. And the process variable also given to the controller. It finds the difference and gives 420 milliamps according to level. If you consider this part alone, that is called flow process. Here what we are doing, actually to control level, we are controlling the flow rate. In some process, we have to control flow rate. Sometimes we have to control the flow rate. In that case, what is the process? Process will be looking like this. Process will be looking like this. Through this, some flow rate is there. For example, a diesel engine. Diesel engine has to be, the speed has to be controlled irrespective of load. Have you noticed that if load increases, speed will decrease? Have you noticed? Suppose you are cycling. Somebody suddenly sits on the back seat. What will happen to the speed? Speed will decrease. Like that, if you turn on many lamps, the alternator speed will decrease. Alternator speed will decrease. It should not decrease. It should run at the same speed. Why? Because what is the frequency of power supply? 50 hertz. That's why it should rotate at a constant speed. Then only you will get 50 hertz. Otherwise, you won't get 50 hertz. So, irrespective of load, it should rotate in the same speed. That's why a controller is required. So, that will adjust the, suppose the generator is run by diesel, means it will adjust the diesel flow rate. Example I am telling. So, this is such flow pipe. In that, I want to control the flow rate. To control that flow rate, one valve is there. This valve has to be adjusted to adjust the flow rate. So it has to be measured. It has to be measured. For that, this is orifice plate. You might have studied about orifice plate in the industrial instrumentation. 2 tappings are taken before that orifice plate and after that. And it is given to the DPT, differential pressure transmitter, that gives the flow rate. That flow rate is 4 to 20 milliamps. 100%, 0 to 100% is represented by 420 milliamps by this DPT transmitter. The flow rate we are getting, that should be given to the controller, PID controller. For the controller, we are giving set point also. Set point means what flow rate you require. 50% flow rate is required, I may say. So here also 50% means no problem. Otherwise, the controller will adjust the valve opening. So this is, its output is 4 to 20 milliamps. This 420 milliamps has to be converted into 3 to 15 psi. Again, 3 to 15 psi. That 3 to 15 psi is connected to this valve. So the valve means like tap at your home. In the tap, you have to rotate to adjust the flow rate. Here, we have to give pressure signal that varies from 3 to 15 psi. That the flow rate will vary. The flow rate coming out of this will vary. That's all. This is the flow process. This is conventional flow process. But in the lab, it is slightly different. Here, the problem is here, how the flow rate is adjusted here. The flow rate is adjusted by this valve opening. The valve, if you close, means it increases the resistance. It increases the resistance to flow rate. That's why flow rate decreases. But a pump here always pump the same amount. But because of the resistance, flow rate decreases. It means the pump has to spend same amount of power, irrespective of flow rate. Suppose flow rate is always 50%, means the pump has to spend 100% flow rate power, but it uses only 50%. Power is wasted in the lab, wasted in the valve. It dissipates power. This valve dissipates power. This valve absorbs some power because of by introducing resistance. That's why there is a large power loss. In a small tap, small power will be wasted. Suppose in the industry, suppose they are using 100 HP motor. 100 HP motor means 8,000 something power watts. 50% of the power, 50% only you are allowing flow rate, means the 50% of the valve is closed, but the pump can pump 8,000 watts. That much flow rate it can deliver, but only 4,000 watts is used. 4,000 watts is wasted. So nowadays, these are all valves are replaced by variable frequency drive. That we will see now here. Variable frequency drive. So instead of pumping same amount, instead of valve, it is replaced by, this is coming from sump. This is the sump from where we are getting the liquid. This is the sump from where we are getting the liquid. Here we are putting a pump. Let us put like this. This is the pump, or we can put a box shape pump. A box, and it is a pump. This pump speed can be varied. The pump speed can be varied, so that flow rate can be varied from 0 to 100%. Flow rate can be varied from 0 to 100%. Flow rate can be varied 0 to 100% by adjusting the speed of the pump. For that, again we have to measure the flow rate. A RFI's plate is there. The tappings are taken. A differential pressure transmitter gives 4 to 20 milliamps. That is given to a VFD. That is called VFD. That is given to the 420 milliamps is the cross variable. Actual flow rate is measured. That is cross variable. Set point also given to the controller. This is the controller. That gives again 4 to 20 milliamps. If 20 milliamps it gives, the pump has to run at full speed. 4 milliamps given, pump should be stopped. So its speed varies from 0 to 100%, depends upon this 4 to 20 milliamps. That 4 to 20 milliamps, how to vary the pump speed? How it can be varied? For that pump, one 3-phase motor is there. It is coupled with the pump is just, it will rotate and pump the liquid. That's all. But it should be rotated by a motor. Rotated by a motor. A motor is connected. A 3-phase motor is connected. 3-phase motor is connected with that. If the speed of the motor changes, pump flow rate will change. Am I correct or not? So how to change the speed of the motor? Speed of the motor is function of what? N is proportional to three-phase induction motor. Speed is proportional to what? Have you studied the formula in electrical technology? 120 F by P. 120 F by P, where P is the number of poles in the motor, N is the speed of the motor, 120 is constant, F is the frequency of power supply. If you are able to vary the frequency of, but here what we are getting is constant frequency, 50 hertz. That's why if you give that power supply to any motor, the motor speed will be constant. Motor speed will be constant, but we want to vary according to 4 to 20 milliamps. That's why a device called, a power electronic device called VFD, variable frequency drive. To that, this 420 milliamps given, that gives a three-phase power supply. That gives a three-phase power supply to this motor. Its frequency varies from 0 to 60 hertz, 0 to 50 hertz or 60 hertz, depends upon the. Let us assume that the motor runs at 60 hertz. So 0 to 60 hertz in UK and Canada's standards are 60 hertz. But Indian and UK standards are 50 hertz. So it's 0 to 60 hertz power supply. It will give constant voltage, but frequency is varying. Its output depends upon 420 milliamps. I will say this way. If 20 milliamps is given 60 hertz, 4 milliamps is given 0 hertz. So it frequency varies from 0 to 60 hertz. That VFD will give. That's why the pump speed will be adjusted. This is the experimental setup available in the lab. So the valve is replaced by VFD. This, by using this, we have to adjust the flow rate 0 to 100%. 0 to 100%. I want to do control. For that, here I am using a PID controller. Here I am using a PID controller. PID controller means controller output M equal to what? M equal to Kc multiplied by error plus Kc by Ti integral of E of t dt. That's all. PI controller. Let us use not PID, PI controller. Let us use. PI controller is used. That's why this plus bias. Always bias is required. Already we have discussed why bias is required. Suppose the car is running at 60 kilometers per hour. Are you giving any input, or because of zero error, you are not giving any input? You must give some input to run at 60 kilometers per hour. The same meaning here. If there is no error, means that time it should give something to get the required output. For that, that bias is required. Controller will not find the bias. We have to find the bias. That bias will controller add and it will give. In the previous class, I said if you transfer from manual mode to auto mode, what is happening? What I told you is this formula is implemented in the controller that I told. Before that, what is that? M equal to bias only. Before that, M equal to bias only. It means in manual mode, we are adjusting the bias. Whatever the controller output in manual mode will be included in the auto mode. This is the controller output in auto mode. Auto mode means closed loop. Closed loop. Manual mode is M equal to only bias. Bias is adjusted. Manually, we can adjust the value. But in closed loop, it is constant. Bias is constant. This part becomes constant. You cannot adjust it. If you press up down arrow, you cannot adjust. Which part adjust the controller output? This part. This is the variable part. In controller, this is the variable part. This is constant part. In closed loop, in auto mode. In manual mode, this part is 0. This part is 0. This part is 0. No, error is not calculated. Error is not accounted. Always error 0 in manual mode. Error will not be taken into account. Only bias can be adjusted. This is variable in manual mode. So in manual mode, we are adjusting the controller output manually and gives the required controller output so that we will get 50% output. Suppose set point is 50% means we are adjusting in manual mode to get 50% output. 50% output we adjusted. If you transfer from manual mode to auto mode, that you gave something in manual mode, no, that becomes constant there. That becomes constant there. I didn't explain this part in the previous class because I don't want to make you confused. Now you will get some idea. That's why I'm telling now. So what is happening while transferring from manual mode to auto mode? This formula part is included by making bias equal to constant. By making bias equal to constant. That is the function of controller. That is called bumpless transfer. If you do the bumpless transfer means transferring from manual mode to auto mode. If you transfer from manual mode to auto mode, the bias becomes constant and the formula part as function of error is included in the controller output. That's all. Now, what we have to do, tuning means what? We have to find Kc, Ti we have to find. We have to find Kc and Ti because it varies from process to process. In the previous class, what we have seen is level process. Its mathematical model is different. Its time constant is very large. Its time constant is very large. But in flow process, time constant is negligible. Like electronic process, time constant is negligible. Here, time constant is in very, very small. So, you cannot use the same Kc and Ti here. You have to find a different time constant here, different tuning parameters here. You have to find different tuning parameters here based on this process. How to find that?